Section 2.5 covers the derivatives of composite functions. So composition is the process of combining functions. So we have the definition of a composite function is given two functions, say f and g, the composite function of, and its notation as f, and then there's usually either a circle or a dot. So f circle, g is defined by the composite function of f and g at x equals f g at x. So basically what we're going to do is we're going to substitute g at x, which is like that second term here, into f. So let's go ahead and just practice this skill. Okay, if f at x equals root x and g at x equals x plus 5, then find the following values. So for this, f at g at 4, we can just solve for g at 4, which is 4 plus 5, which is 9. And then what we can do is solve for f at 9, which is root 9, which is plus minus 3. Okay, g at f at 4. So let's just do f at 4, which I get plus minus 2. And then g at 2 is 2 plus 5, which is 7. And then g at negative 2, which is negative 2 plus, oh, sorry, this is supposed to be 5, equals 3. Okay, now let's just sub in g at x into f. So this equals root, and then instead of putting in x, we write in x plus 5. Now let's sub in f at x to g. So g is root x plus 5. So we're instead of putting, sorry, x plus 5. So instead of putting x, we're going to put root x and then plus 5. So just a little bit of a review. Okay. As for the chain rule says that the derivative of a composite function is the product of the derivative of the outer function evaluated at the inner function and the derivative of the inner function. So again, derivative of the outer function evaluated at the inner function times the derivative of the inner function. Okay, if you want to proof, it's on page 100. I'm going to skip the proof right now and I'm going to go straight into questions. Okay, let's differentiate h at x equals x squared plus x to 3 over 2. Okay, so this is power rule. We bring down the 3 over 2. We write the bracket as it is. And then we subtract 1. So we get 1 over 2. But we're not done. Because what we want to do is we want to evaluate, like, this equation is actually a composite function. So f at x would actually just be x to the 3 over 2. But what we did is we subbed in, instead of writing it as x, we subbed in x squared plus x. Okay, we saw this back in, I believe, 2.3 in the product rule. Okay, but now we're formally doing it. So now we have to multiply this equation by the derivative of the inside, which is 2x plus 1. This right here, that's considered the chain rule. Now we can also do the chain rule in Leibniz notation. Okay, if we interpret derivatives as rates of change, the chain rule states that if y is a function of x through the intermediate value u, then the rate of change of y with respect to x is equal to the product of the rate of change of y with respect to u and the rate of change of u with respect to x. Okay, super confusing, but this is basically what we have. dy by dx equals dy by du by dx. And see how these two cancel? Of course, this is equivalent to dy by dx. So let's use this definition to actually solve for example 3. Okay, if y equals this, so we have y in terms of u, where u equals this, so we have u in terms of x, find dy by dx. So dy by dx equals, let's find first dy by du, so 3u squared minus 2. Now we're going to do du by dx, which is, this is 2x the 1/2. Bring the 1/2 down. We get 1x to the negative 1/2. And what we want to do is we want to evaluate this at x equals 4. Okay, so it may look a little confusing because we have this in terms of u and this in terms of x. So really, if we did dy by dx in terms of 4, we can't really solve for the u's because it's x equals 4. So 4 to the negative 1/2, this is just 1 over root 4. So I get 1 over 2, right? So we get 1 over 2. But what we actually have is we have u in terms of x. So u equals 2 root 4, which is 2 times 2, which is just 4. So we can actually do this one on the side here and then sub it in here. So I get the answer as 2. Oh, sorry, missed a step. So u equals 4. Sorry. Then we sub in this 4 squared minus 2. My mistake. Okay, 4 squared is 16. 16 times 3, 48. So we get 48 minus 2 and then 1/2. I get 46 divided by 2. I get 23. So sorry, the answer is 23. Okay, example 4. An environmental study of a certain substance, or sorry, certain suburban community suggests that the average daily level of carbon monoxide in the air takes the form of this equation right here. I'm not going to write it like that. 0.5 p squared plus 17. Okay, so where C at P is in parts per million and population P is expressed in thousands. That's always important. It's estimated that T years from now, the population of the community will be, this equation, 1,000. At what rate will the carbon monoxide level be changing with respect to time 3 years from now? Okay, so at what rate will the carbon monoxide level be changing? So we want dC by with respect to time. Okay, here's the problem. We have C with respect to P, so we'd have to do the derivative of C with respect to P, and then multiply it by, we also have PT equals 3.1 plus 0.1 t squared. We also have dP with respect to time. Okay, if you remember from the last part, these two will cancel out. We will get dC by dt, but we won't cancel them out yet. So dC by dt equals, let's solve for the first one. This is the 1/2. Okay, the derivative of the first thing is 1/2, 0.5 p squared plus 17 to the negative 1/2. And this is all multiplied by what's in the bracket, the derivative in the brackets. 2 times 1/2 is just 1, p. So that's dC by dP. The next one, 3.1 goes down to 0 plus 0.2t. That's dP by dt. Now, it wants us to evaluate at t equals 3, because 3 years from now. Okay, so we can simply sub in 0.23 right here, but we can't do that with C at P. So what we have to do is we need an expression for time. Okay, so P at 3 equals, because we want P because we have to sub in P to the dC by dP. Okay, 3.1 plus 0.13 squared. 3.1 plus, that's 9, 0.9, so I get 4. So simply, I'm going to plug in 0.5, 4 squared, plus 17,